of 10 to the 9, 10 to the 10 solar luminosities, which is why if a supernova occurs in any given galaxy, it's quite prominent because it outshines the rest of the galaxy. So these eruptions, these luminous red novae, are not as bright as supernovae. So they're somewhat their luminosity is intermediate. What was also observed was a rise in temperature, and then eventually post reaching the peak luminosity, the object began to cool down, and eventually, as V838 Mon cooled, its spectra, the features present in its outer atmosphere, those began to change. And so, if I'm using a lot of astronomy jargon, please feel free to jump in at any time for a clarification. But its spectral type evolved from that of an early type star to a later type, an L-type supergiant. To be specific, its spectra eventually started showing prominent molecular lines, and molecular lines generally mean that are signifying that dust has been formed. That's also something that was seen in the spectra of V838 Mon, that eventually, after the outburst, the infrared part of the spectra became more and more bright and prominent. So at the time, there was a lot of debate and discussion as to what this event was, what caused this eruption. Various scenarios were proposed. One of them was that of a classical nova. So a nova is a binary system where you have an evolved star and a compact object, a white dwarf. And there's accretion of material onto the white dwarf, and that causes eruptions, and the white dwarf brightens by many orders of magnitude. The nova hypothesis, although it seemed to have some promise, but it interestingly predicts an X-ray component, which was not seen in the case of V838 Mon. Another scenario was that of an AGB star. So an AGB star is an evolved massive star where the core is using elements heavier than hydrogen. So generally, an AGB star would have heavy core, and on top of the core, you would have multiple layers. If it's massive enough, then you'll have layers, and then eventually iron will form in the core, and that's when supernova occurs, a type 2 supernova. So anyhow, another scenario was that perhaps one of the layers inside an AGB star went off. There was a reignition of one of the layers. That also had some problems. It wasn't adequate to describe the outflow velocities, and also some peculiarities in the light curve in the luminosity of V838 Mon. Another very interesting scenario was that of planets being eaten. So somebody suggested, I think this was back in 2004, that perhaps what happened was that you had a system where the star evolved, it expanded, and it engulfed its entire solar system. If you look at how the luminosity changed over the course of the eruption, you see this bright peak, and then you also see these smaller peaks. There are two smaller peaks in the luminosity curve. So the planet hypothesis was so it was presented taking these bumps into consideration, that perhaps these smaller peaks are P corresponds to a planet being devoured by the system. However, even the problem with this, there were issues with this scenario as well. So it wasn't able to predict the peak luminosity, and so the scenario that was proposed by my supervisor, and that's that currently, as of now, it seems that it's the best running hypothesis, is that of a stellar merger. So I'll explain what this is. So in 2006, Delinda and Soker proposed that what occurred in V838 Mon causing the eruption was a stellar merger. And in particular, one of the components was a 0.3 solar mass young stellar object, so a newborn star. and it merged with an 8 solar mass, so 8 times the mass of the sun, main sequence B-type stars. So if you're familiar with very basic astronomy, stellar types have these letters associated with them. So it goes from O all the way to M-type stars. And so you have O and then B-type stars. The B-type stars are extremely hot, tend to be blue, and are also many times more massive than the sun. So Tanenda and Soker basically they showed in this in their 2006 paper that you could reproduce all of the observed properties. So the temperature evolution, the luminosity evolution, the size evolution, the speeds of the outflows of the ejecta, if you invoke this stellar merger hypothesis. Generally, how does this ensue? It's thought that within a binary system, if you have as in this case, you have a large star and a smaller star. So the larger the star is, the faster it's going to evolve. It's going to eventually expand and engulf its smaller companion. And this stage where you have this where the larger star has engulfed the smaller one is called the common envelope phase, because effectively they're sharing an atmosphere. And basically, if you have something that's orbiting within this medium, you're going to get tidal dissipation. So orbital energy is going to decrease, and that's going to cause the orbit to shrink, and eventually an in spiral, which is thought to have caused the eruption in V838 Mon. So this is just a sketch of the system. You have the remnant here, and interestingly, it's thought that the merger has it occurred in a triple system or in a hierarchical triple. So currently, you have this red dusty merger, and it's separated. It's orbiting. It's in a binary with another B-type star, so not the one that we think merged before. So what this means is that you have this triple system, and then the inner binary merged, but you still have a binary system. It's since the eruption, the star itself, or the newly formed star, or the merged star, whatever you want to call it, it's considerably less bright in the optical, but it's become more and more prominent in the infrared and radio bands. So generally, if you have something that's dusty and red, it's a good candidate to study using interferometry, especially mid-IR, optical mid-IR interferometry. Because what you can't see in the optical, you're certainly going to see something in the infrared and all the way up to the radio. So there were three main questions that I sought to answer as part of my dissertation. The first one was can we use interferometry to figure out what the structure of this object looks like, the circumstellar environment, right? What dusty, clumpy, is it some other exotic morphology? The second question was what potentially could be going on, what physical processes might be occurring in that circumstellar environment? And lastly, using those observations, is it possible to, construct a physical model using a radiative transfer modeling? So just to give a very brief primer on interferometry, interferometry differs from standard imaging because if you have a single telescope or a camera or your eye, you're directly recording light from an object. So you're directly imaging the source. What's different in interferometry is that you have two or more than two telescopes. And the idea is that you interfere light from a single source. And so what you get is not an image, but in fact, you get a fringe pattern. It's very similar. In fact, it's the same principle that's used in the double slit experiment. And so you have fringes, and you need to somehow go from fringes towards an image, which is challenging because you have constructive and destructive interference. So you've also lost some information. But the idea is that using within any interferometric configuration, because you can space out telescopes, so it's also possible to obtain information on details that otherwise would not have been possible with just a single telescope. So the the joke is, and this is I mean, this analogy has been used to death, that you take two telescopes, you combine them, and you get a larger telescope, right? That's that's the that's the go-to layman explanation. But it's entirely, I mean, it's not entirely wrong. There is some merit to there. All right. So prior to the commencing of my PhD work, there were these two studies that were done on V838 Mon. The one on the left was done using this Palomar testbed interferometer, which was just a two telescope interferometer. And what the authors did was that they were able to measure the size of the object of V838 Mon. And on the right is the 2014 study by Olivier Chestnut. What Chestnut did was that he again was able to get some rough size constraints. What he found that in the if you look at V838 Mon, again, when I say look, I mean if you study it with an interferometer using so he used these old generation instruments. He found that there's this elongated dusty structure from 8 to 13 microns that seems to increase in size as you go towards longer wavelengths. And so using these as a basis, of course, my job, or what I sought to do, was to use the even newer, at the time newer, instruments in order to figure out, well, what is how similar, dissimilar do my observations compared to what's been done before. Here's another example. This is, again, it's the same V838 Mon system, but imaged using ALMA. So ALMA is this radio interferometer that's located in the Atacama Desert. And this was done by my supervisor a few years ago. And what he found was that if you look at the structure in the radio, so this is I believe this is at this millimeter, yeah. So you see this clumpy extended structure, and so this is the dead center, the merged star, whatever has formed, the aftermath of the merger. Then here's that binary star, and there's this like weird wake-like feature. All right. So the work that I did was, you can think of it this way, that I sought to zoom in into this like very into the inner environment of V838 Mon. And so that was the subject of my first publication. So back in 2020, when I started my PhD, it was also the pandemic was going on. So initially we were scheduled to take many observations with an instrument known as Matisse at the VLTI. So the VLTI stands for Very Large Telescope Interferometer. So if you look at this picture, you see these larger telescopes. These are known as the unit telescopes, and then you see these smaller 1.8 meter telescopes. But these are the auxiliary telescopes. What I did, all of my research relied on the auxiliary telescopes, and essentially the advantage of using these telescopes is that you can change the length of the baselines. So that gives you something that's known as better UV coverage. I'll explain what that is in just a minute. The longest baseline on with the VLTI is about 140 meters. So if you're familiar with radio interferometry, the largest baselines on radio interferometers tend to be very large, like tens of hundreds of kilometers. So for example, in the case of the Event Horizon Telescope, I think the largest baseline is like 6,000 kilometers. That's the radius of the Earth. Unfortunately, we can't really do that in the L band. So starting off from so from 3 to 4 micrometers. The issue with this mid-infrared part of the spectrum is that you can't, if you space the telescopes too far, you're not going to be, so you won't be able to cohere the light, which is essential if you want to produce fringes, right? Because you can only get destructive and constructive interference if you have coherent light. So in any interferometer, you'll have what you do is you focus, so you get a fringe pattern, and then the fringe pattern is recorded onto it's produced on something known as a beam combiner, which is just a fancy way of saying that you take light from all of the telescopes and produce a fringe pattern, record the fringe pattern, and then using the fringe pattern, you work backwards to figure out what the source looks like. So the Matisse instrument works in the L band, 3 to 4 micrometers. What I'm showing you on the right are the UV tracks. So if you look at, so in any interferometer configuration, you're going to have these telescopes. Each telescope has a baseline vector associated with it. So of course, the length of the vector is just the distance between the telescopes. And then of course you have, there's going to be some direction. If you project those baseline vectors onto the sky, onto a system known as UV coordinates. And so really the gist of this is, the thing to remember is that the more sampled your UV space is, the better your image will be. So the more poorly your UV space is sampled, the worse your image is going to be. So what the issue we had, we only had 2 nights of good data in 2020. So that's at the time, we thought it's probably best to not proceed with imaging, and let's try to see if we can indirectly figure out what the source looks like. So there are these 2 observables that you obtain from the fringe pattern. One of them is known, it's the squared visibility.
What do you call a fringe pattern? What is a fringe pattern?
Oh, fringe pattern. It's like
fringe pattern.
Yeah. Sorry. I'll try to speak a bit more clearly. Yeah. So from the fringe pattern, you get these 2 quantities. On the left, I'm showing you the squared visibilities, and on the right are the closure phases. Very simply, you can think of it this way, that the power of the fringes is stored in the squared visibilities. So that both of these quantities are plotted. So they're plotted as functions of the spatial frequency. And the spatial frequency, the larger the spatial frequency, the larger your baseline. So mathematically, it's the baseline divided by whatever wavelength you're observing at. And the thing is that in order to get an estimate of the size of the source, you need to be able to reduce the squared visibility. So wherever it drops to 0, that's where you get the first 0. That's the size of that's how you can get the size of the object, because that's the baseline at which the object has been resolved. So squared visibility of 1 means it's poorly resolved. Squared visibility of 0 means it's very well resolved. On the right, we have closure phases. So an issue with measuring phases using interferometers is that you're going to have some intrinsic, you're going to have turbulence, some systematic that's introduced by each telescope. If you have 3 or more telescopes in each triangle, what ends up happening is, because of symmetry, the effects, the atmospheric effects cancel out. And so you're only left with the intrinsic phase of the object. And that's important because if it's 0 or 180, that means your object is perfectly circular on the sky. If it deviates from 0 or 180, so for example, if you look at these preliminary closure phases, you can see that they're not effectively 0. You have a few degrees of variation, especially if you look at the longer baselines. So you can ignore the points that are way off here because the error bars are too large. And that's important because that means that the interferometer is picking up some asymmetry. So now that begs the question, what's the nature of that asymmetry? And that's really, I'll talk more about that as we go on. So a thing that you can do, I know there are a lot of plots, but What we did was that we said that, okay, well, we have these quantities, right? We've extracted the squared visibilities and the closure phases from the data reduction pipelines, and these are each instrument on the VLTI has its own dedicated data reduction pipeline. You can install them on your computer. They have a bunch of manuals and tutorials. But what we thought is that let's try to figure out what intensity distribution on the sky could perhaps best reproduce the observations. So what an interferometer does, another way to think about this, is that it's measuring the Fourier transform of the object's intensity on the sky. So what we have is the Fourier transform, and we want to we basically want to ask the question: what intensity distribution must have resulted in that Fourier transformation? For example, you can usually there are these like building blocks that you start off with. I've left out lots of details of the softwares, but you can either do this yourself, try to start with some intensity distribution. So, for example, a uniform disk, and then compute its Fourier transform, and then see how that compares. There are lots of dedicated tools that the optical infrared interferometry community has developed. And really, what all of those tools do is that you start with some intensity distribution, you compute its Fourier transform, and so you actually compare the simulated, or the theoretical squared visibilities and closure phases with the observations, and try to see which one matches the best. So I'm showing you a lot of models. So what I did was that I used various combinations of disks and Gaussians and point sources. So a disk, the Fourier transform of a disk is a Bessel function, and then for a Gaussian, it's just a Gaussian. For a point source, it's actually just a flat visibility of 1. So in this early study, I found that some of the models that worked really well with fairly low chi-squares were these models where I had an extended feature, so either a Gaussian or a disk. This is just a schematic, a diagram, and with point sources. So if you had 2 point sources, we found that the models would fit the observations even better. But of course, there were at the time there were several limitations. First off, we only had 2 nights of data. Second, if you make a model more complicated, it's obviously going to represent the data even better. That's just because the Fourier transform will just become more and more complicated. You'll have more components. So we thought that, okay, well, perhaps doing just this exercise, there's potentially there might be symmetries in V838 Mon, but we'd like to explore this further. We'd like to image the source, right? Seeing is believing. So, but before we go on to the imaging, what I'd like you to focus on is that all of the observed features in the radio all the way up to the infrared are plotted on this diagram. So the one that in this study, what we were probing was this blue or cyan region. So it's really right there next to the whatever has formed in the aftermath of the eruption. Whereas everything else it's quite spread out. So moving on to imaging, so we applied for more time on the VLTI. Previously I mentioned the Matisse instrument, another instrument that we used in this study. The one that we used for imaging was gravity. It's I don't know why it's called gravity. Usually you have these very cumbersome acronyms in astronomy, but this is not an acronym. It's just the name of the instrument. It works in the K-band. So the K-band goes from 2 to 3 micrometers, again, on the same of these smaller auxiliary telescopes. In addition to the VLTI, we also used the CHARA interferometer, which is located in the US, in the state of California, on in Mount Wilson Observatory. So if you're familiar with the history of Mount Wilson Observatory, it's where the 100-inch Hooker telescope used to be that Hubble used to measure the redshifts of galaxies. So the advantage of using CHARA is that the longest baseline on CHARA is about 3 times larger than the longest baseline on the VLTI. So the larger your baseline is, again, think of the interferometer as one giant telescope. So the larger the baseline, the larger the telescope, the better your resolution. But now an issue in interferometry is, well, how does one go from these discrete observations on to, and then of course produce a continuous image? Because as I showed you before, like if the UV plane has tracks or points, and then you have all of these, you have missing information. And of course, an image it has to be continuous, right? You can't have these discontinuities. So the imaging, interferometric imaging is usually it's termed as an ill-posed problem because you don't have enough data points. The number of data points does not correspond to the number of parameters in the image that you need. So you need to fill in these gaps, and the way that's done is you have to assume the behavior of the image. There's many ways of do that. I won't go through the details of all of that, but in the interferometric community, the optical near IR interferometric community, there are various algorithms that people have developed for imaging. Again, the differences are in basically how they fit in this space. And so the way to do this, or at least to do somewhat reliable imaging, is to rely on more than one algorithm, just so you can try to figure out what are artifacts and what are actual features in the image. Secondly, you choose, once you practically start to do this, you have to choose something that's known as a regularization. So the regularization really just weighs the model with the data. And so what you're doing effectively is you're reducing or minimizing a cost function. So how much weightage do you give to your chosen model as opposed to how much weightage do you give to your data? Then, of course, this is a very important step. You have to set the pixel size and the field of view. So rule of thumb is that for any interferometer, the best pixel, the pixel of your image would be the angular resolution that's obtained with the largest baseline. So lambda over b would be the largest baseline. In the community, it's you can actually go below that. So there's a rule of thumb that you go for lambda over 4b. And the field of view is just the field of view of a single telescope. That's the field of view of your image. But of course, there are also practical considerations. So for example, I'll talk about the size scale. What we have is something that's very, very compact and not very spread out. So of course, using the whole field of view, it won't really do you much good. If you want to try to figure out what the morphology of the image is. And then finally, of course, you produce an image. So what I'm showing you here are imaging results using the gravity instrument. So the image on the left was made using pixel size of 0.5 milliarc seconds, and the one on the right was made using the pixel size of 8 milliarc seconds. And it's good to make multiple images using different pixel sizes, because, for example, if you go for a smaller and smaller pixel size, there's a chance that you might end up producing artifacts, or you might end up confusing yourself. So if you go towards higher and higher pixel sizes, and if you still see maybe not everything, but at least some semblance of consistency, then that means that what you're seeing is potentially a real feature. So what we see using the the gravity data constructing the image is this elongated bipolar structure. So I should mention that this whole structure spans about 3 milli-arc seconds. So an arc second is 1/3600th of a second. So a milli-arc second is a thousandth of that. For example, if you recall the black hole image, the one of M87, I think the angular size was 40 micro-arc seconds, right? So that's even smaller. Which is why, of course, you need such a huge interferometer to resolve those photon rings. So anyhow, here, of course, a milli-arc second is also it's pretty small. And here are the imaging results using the MERC-X instrument on CHARA. So the CHARA data are in the H band. I know I'm throwing out a lot of letters. The H band goes from about 1.6 to 1.9 micrometers. And once again, the image on the left is 0.2 milli-arc seconds, the pixel size, and on the right is 0.5 milli-arc seconds. If you look at both the images, the north, so you again sort of see something that goes from this northeast to northwest position angle. And the northern component is a bit bent compared to its southern counterpart. So, and it's interesting because it seems that there's a stronger asymmetry in the H band. And remember that the CHARA baselines are a factor of 3 larger than the longest VLTI baseline. So that means that the CHARA as an interferometer is a lot more sensitive. It's picking up on features that are otherwise not picked up by the VLTI. So it's interesting.
Can I ask a question on your last slide?
Go ahead.
How hard is it, or how long does it take to generate one of these pictures?
So
you have the data.
You can do it right away, but the thing is that it takes time to figure out, for example, what regularization you want to use. What value for example, the hyperparameter. So that
let me just ask what I have in mind, and perhaps you can address.
Go ahead.
So would it be better to, let's say, do it for some more values between these two sizes of pixels, just so that you have a more robust idea of what the physical features are?
I mean, I did that. I mean, that was it was a lot of, so generating like a single image is not too it doesn't take too long. It's just that you have to generate a lot of images to try to, and also what I also did, I'm not showing it here, but it's in the papers that we also used. So we did try a bunch of other algorithms, but we ended up focusing on 2 of them. One of them is called Myra, the other is called Squeeze. And so it's not only just generating images, it's also using different algorithms to generate the same images. By same, I mean like the same pixel size. And then, as you said, like also, so for example, we also tried, it's in the paper, but it's not something that we use to in our analysis. So I also generated an image at 0.1 milli-arc seconds, and that looks completely, I mean, sure, you still have like this elongation, but maybe I can show it to you later. It had these like clumps, but of course, 0.1 milli-arc seconds for both these interferometers is pushing the limit, like a realistic. So 0.8 milli-arc second is a more realistic pixel size for the VLTI, and 0.2 is also, so 0.5 is like the best achievable resolution with CHARA. And so 0.2 is still, you can go slightly below. So remember, like lambda over 4b. But you're right, like that is something that we did. So not just like within this range, also like what happens if you go beyond. Of course, if you go beyond the theoretical the worst resolution of an interferometer, then of course you're going to get nothing because it'll just get cleared out.
Well, Zain,
Did you?
when you have like the data and you are seeing that you have option to choose an algorithm because there are many possible algorithms. And I assume that different algorithms generate different images. So how do you decide, which image is a better representation of the real object?
That's a good question. So a while back, there was this. There's actually a paper on this, an interferometric beauty contest. So what happened is that participants were told that you should use all of the available algorithms, try to see which of it produces image that you would trust or that you think is the most reliable. So if if your data is all right, if it's not if there are no issues, you should generally see the same structure in each image. Of course, there's going to be some differences. For example, there's one of the main differences is how the space is filled. So, for example, one algorithm might do it some way, another might do it in some other way, and that tends to produce. I'll use perhaps a different texture in the images. So maybe you'll have one where the spaces sort of blend in, another where it's maybe not. It's quite like you have sharp edges. So that's really what. So you shouldn't. We don't expect if you use different algorithms that you'll see something completely different, like a disk in one, and then perhaps maybe a circle on the other. That shouldn't happen unless your data is pretty bad. And so it's been there is work on this, but generally these algorithms,
even if you're like similar but still different, so how do you decide which one to go with? And also, is there any measure that quantifies the amount of uncertainty with the data after the image has been generated?
Yeah, so in terms of like how you decide which to go with, it's really so once you see in your images that there is this one feature, although not identical, but for example, in this case, in V838 Mon, with the other algorithms, what we saw is that okay, we certainly get something that goes along this position line, right? Now there might be like differences in terms of or maybe this is a lot more. The pixels are a lot more boxy here. In some other algorithm, they're probably blended a lot better. But that's really not because if you think about it, even these like very smaller at the pixel scale, you're also dealing with like with sizes that are technically much smaller than the interferometer should be able to do. So should be able to resolve.
I'm asking because this looks like a machine learning problem, and in machine learning algorithms, there are ways to benchmark the algorithm.
So the way that the algorithms do it is that they effectively they reduce something that's known as a cost function. So there's this penalty associated with the data, and then a penalty associated with the initial model that you start with. So, for example, if you were to start with, say, a disk, you're more likely to get something that's going to look disk-like. So, what we do, and it's described in the paper, is that we started off with a random distribution. So, you generate in each trial, you start off with some randomly generated image and use that as your starting, as opposed to unless you for some reason a priori already know what the morphology of the source is going to be.
Because in this case, I assume that you also have data from other observations. For example, there might be images in another frequency, maybe direct images.
There are. So, but the issue is that they don't. So those are different scales. So, for example, in the radio. So this is a few milliards seconds. In the radio, it's a few hundreds of milliards seconds, right? So it's not. So if I go back, so these are all of the structures that have been observed so far, right? So this is the one that we were probing with the images, but then you have, and this is just I've just made a cartoon. It's not like if you recall the Alma image that I showed you earlier, it had this like very clumpy distribution. So yeah, so basically, yeah, go ahead.
Okay, keep going.
Right. So what potentially could be an explanation of this, and we were of course just speculating. But if you look at other merger objects, they tend to have this pronounced bipolar feature. So, for example, on the left, this is a reconstruction of V838 Sagittari, which is another merger object, and so it has this. My supervisor found that an hourglass morphology tends to represent this well. For example, if you've seen like images of planetary nebulae, you see that they have this like diverse range of morphologies, and there is this hourglass feature that pops up, which might have to do with potentially maybe a circumbinary object, a circumbinary disk, or a binary object. Something similar is also seen in the Blue Ring Nebula, which also has these conical outflows. The authors, at least they think that the spectra is best explained by conical outflows. The image on the top right is of CK Vulpecula, and then of course we have one of my colleagues, Tom Steinmetz. He also found that in another stellar merger object, V1309 Scorpii, it's best explained by its spectra is best explained by a bipolar outflow. So there's also lots of theoretical studies that for example, during the common envelope stage, in order for the object to eject the common envelope, the formation of a jet is essential because it's going to unbind, it's going to add energy to the surrounding envelope. So it's interesting that V838 Mon seems to be showing something that is potentially similar. Of course, all of these are distinct in their own right, and they're going to vary. But you certainly see this bipolar structure occur again and again in merger objects. So finally, we wanted to do some. So we wanted to see if we could use the observations to inform us in our radiative transfer modeling. So radiative transfer is really just how light propagates in any medium. And what we did in this final publication of my thesis is that we constructed, so we wanted to, so we started off with some theoretical dust distribution. We simulated the environment of V838 Mon. So basically said that, okay, well, let's assume we have a point source. That's where we're getting the radiation from. And then let's surround it by some dust. Now, of course, the dust that we used, the distribution that we used, consisted of amorphous silicates. And we didn't really. So the goal was to see if using that, using various dust distributions and morphologies, can we get a simulated image that then compares well with with the observations that we have. So in a sense, what we're doing is that in our model, in our simulation, we're putting all of this theoretical dust. Then we're doing the radiative transfer, doing the ray tracing, and then we project the simulation or the simulated environment onto the sky and get a synthetic image. And then the synthetic image is compared with the observations. So this is what the model looks like. Again, there were many models. I'll show some of them in an upcoming slide. But the one that we've stuck with in our paper is this 3-component model. So there is this torus like feature. Then you have this inner disk, or an inner disk, this yellowish. So the red dot, that's the star. That's the star in this model was assumed to be a point source. And then of course you have these jets or outflows, whatever you want to call them. And the density is color coded. So what did the synthetic images look like? So what I'm showing you here is a synthetic image in the K band. So you can see that the images. So this is going from our simulation, projecting it on the sky, and then asking the question that, okay, if I'm to observe this this simulated object on the sky with CHARA and VLTI, what would the image look like? So the simulated image looks like this, and from that we can then extract squared visibilities and closure phases. There are lots of steps involved. The details are in the paper, and then try to see if they compare. How did they compare with the observations? So we found that we struggled a lot with trying to figure out trying to get a good fit for the K-band data. So the K-band is, remember, it's 2 to 3 microns. But interestingly, we were able to get a somewhat decent fit to the observations in the H band, which is the wavelength at which CHARA observes. So you can see that the squared visibilities, a lot of them are reproduced. Some of them, of course, are left out. The model certainly has it lags in certain areas. If you look at the closure phases, most of them are observed, but then you have this cluster at the smaller end of the spatial frequencies that are not as well explained. So essentially, we thought that, or we concluded that you can, at least in one of these bands, get a somewhat adequate explanation using this physical model, this 3-component model. In the H band, of course, it's tricky. In the K band, we weren't able to really crack the code here. So we also looked at various other models. In some of these models, we just simply changed the inclination. So remember that we're looking at something on the sky, and we're not entirely sure what the inclination is of so what viewing angle we're looking V838 Mon at, and that's going to cause there are certain biases. So, for example, if you look at something elliptical at a certain angle, it'll appear spherical. At some other angle, it'll look more elliptical. So we also played around with the viewing angle. So the top panel is just like changing the inclination of the disk or the jets, trying to see if that does anything. We found that it does something. It usually the observables that we get from changing the inclination were either nothing happened or something is very strange would happen. You would get closure phases that are hundreds of degrees and funny squared visibilities. The bottom panel is just changing the size of the disk. This, of course, was just something that we did. This was more done in order to see if we can maybe get something better for the K-band. But the issue is that this is really because you can only change the size so much because the physical size is it's about 3 milliards seconds. So obviously, if you have something that's 10 milliards seconds, it's not realistic. But it was more of a trial to see if we can maybe do if there's a way to like play around with this to make it better. So just to summarize, in this study we were able to construct near to mid IR interferometric images for V838 Mon using 2 separate interferometers. We certainly see a feature that's bipolar. Perhaps it's a jet, perhaps it's an outflow. That remains to be seen. In our final publication, we saw that we can use the multi-component, so the torus, disk, and jet model to explain at least the H-band observations. We struggled with explaining what happens in the K-band. And then, of course, this is important because it's thought that merger phenomena might be responsible for producing all sorts of erratic stars, one of them being blue stragglers or rapidly rotating stars or magnetic stars, etc. So it's important to to sort of to study, of course, to study the circumstellar environment, and then try to see if we can figure out what processes are at play. So yes, with that, I will end my talk. If there are any questions, I'd be happy to answer.
Very good. Thank you very much. Questions, please.
Do I stop my session?
No, you can leave it there in case there are questions.
Oh, there is a question.
Yeah.
Most astronomers, they use a lot of models.
Could you repeat the question?
Oh, sure. In most of the astronomy problems, they use a lot of models and simulation. How hard is it to do these many body classical problems analytically? I don't have any experience with n-body simulations. From what I've heard is that I think there are like dedicated software packages that deal with this. I think I think it's called Gadget. That's used for n-body simulations. But yeah, I'm out of my depth here, so I don't want to say anything that.
Well, analytically, it's impossible.
Oh yeah, analytically, of course, you can't do it.
The question is easy. The question is easily answered. Yeah? Analytically, you can't do it.
Yes.
You can't even do the three-body problem. So.
Restricted.
Huh?
Unless under some special circumstances.
Yeah, so you can do special cases. You can do
restricted
special cases
yeah.
for three-body ground. But other questions?
But three body is relatively easy to code.
Oh yeah, coding is a different matter. So there you can do a lot more.
How are these models developed? Data that people have been accumulating, they have developed different models.
Like
Since they are not analytical, so how are they?
Which ones? The ones that I showed?
No, the models to which you are mapping.
Oh, so that's just so you usually you have some radiative transfer code. In our case, we used I can write. So it's called RadamC3D. It's open access. The way you do it is that you pre-fill it with opacities for some material, the size of the dust grain. You can tell the software how many photons, like basically how many clusters of photons you want to use, and then it does like a Monte Carlo calculation. So we were essentially just using it because my supervisor does a lot of these simulations. It's helpful because it's easy to. So for example, you can really there's a lot of geometries that you can explore. And basically within whatever code that you're writing that calls RadamC3D, you just have to specify that, okay, look at this area within or restrict dust to say a sphere of 100 astronomical units, etc. Or perhaps, so for example, in these models, if I go back. So for example, what I had to do was specify this region, specify its density. So there is, of course, a uniform density, but then in each of these individual regions within the code, you can say that, okay, well, maybe boost the density here by this factor and it here by this. So yeah, it's all done like virtually, but you need opacities for whatever dust species that you're using. So if you look at the code RadamC3D, it already has like a library of species, various molecular species. There's also a way to generate your own, where you can generate your own dust distribution. I didn't try that because we thought that let's stick to this distribution that it's they consist of amorphous silicates. But yeah, but these are so the simulation itself takes in a lot of these input files, and then once you call the simulation, a lot of this geometry stuff is something that you do on your own, like defining these regions that let me do the radiative transfer, but do it within a jet, do it within a disk. That's just writing scripts in Python.
How do you decide
Yeah.
Is it a jet or is it a disk?
That's a good question. It's not as straightforward because you can effectively, like, you have you know, like, the sky is the limit. You can come up with whatever crazy observation. But the way we decided was, like, let's look at the images and maybe try to build upon that. But of course, the images themselves are you can see that, yeah,
they're not very perfect.
yeah, that's right. There are limitations in the images as well.
Some things in astronomy seem like, cyclic. You assume this, you do this, and from that you
Exactly.
and then you keep refining.
If you go forward,
Yeah.
If you is this supposed to be a good fit?
No, it's not. That's the thing. Yeah,
Right.
yeah. This is, but this was
This is a good fit.
yeah. But it's interesting because it's not fitting this cluster of at the smaller spatial frequency, and so yeah, it's really strange. Like, what exactly is going on? But yeah, I mean, this is really what you can do. Like, maybe try to put restrictions or narrow down a problem. But there's no one way to do it. It's entirely possible someone else can maybe perhaps approach this in another way. But you're limited by, of course, how many simulations you want to run, and because these take time. Some of them, some of these I had to, like, just let them run for some hours. So yeah, it's time is also another factor. Is there some question?
First from Rizwan and
Yeah, go ahead.
so maybe if you can ask a few questions. Good questions. Yeah. Please, give us more. So there are refreshments. So
I'll ask.
Yeah, go ahead.
So how important are special relativistic and then general relativistic effects in these models?
So general and special. I mean, this is really just so as far as I recall. Well, again, it's just basic radiative transfer. There's no, like, relativistic, because this environment isn't relativistic to begin with.
Right.
Stellar mergers are generally, it's these are sub-relativistic. There's just nothing here. It's not like how you have, like, quasar jets or compact object jets. So, for example, if I go way back, so in the beginning, a lot of people who were trying to posit the Nova hypothesis for V838 Mon, one of the biggest deficiency of this hypothesis was that if you have a nova, you have a white dwarf, a compact object, and it's secreting stuff from its red giant or AGV star. Now, that's a relativistic environment. You're going to have synchrotron radiation, and so you should have a strong magnetic component. But V838 Mon at the time doesn't show a strong magnetic component. In fact, there's no X-ray radiation.
And these jets that you've shown, they're traveling at very low speeds.
Yeah, like I don't want to misquote. Let me go. Oh no, sorry. Do I have it here? So I mean, some kilometers per second. Yeah.
Oh.
Yeah. These are not relativistic at all.
Right.
Yeah. Other questions?
I have, but can you switch off the recording?
Oh, absolutely, we can do that. Oh, is there? I think there's one. Okay, no, that's it. We're done here.